Hi everyone, welcome to the second session of the Diabatix Summer Series. I'm Gert-Jan and I'm your host for today. Today we will be covering one of the most essential parts in simulating and designing, and that's post-processing, and more in detail how you can do that in a time-efficient way with Diabatix ColdStream. It's the second session in this summer series. For those of you who have joined the first series, they know that. For the other ones, during summer we will organize a series of webinars handling different topics. The first one was just about the setup of a CFD simulation in Diabatix ColdStream. Today we will talk about post-processing, and in 2 weeks my colleague Rejma will show you, for one of the cases that we will handle today, how you can design with generative design as well. Last one is the 27th of August. That webinar will be given by my colleague Dr. Van de Beek, and she will talk about applying boundary conditions. So these are the 4 series. So for today we will talk about post-processing, and we will continue on the cases that we have handled in the first webinar. If you don't have followed the first one yet, you can still do that on our website. There is a recording available which you can watch or re-watch if needed. But I will start with a quick summary of what we have done last time. So basically we have started 2 simulations, one about a liquid-cooled cooling jacket and one about a forced-cooled, air-cooled amplifier. So we have done that setup, we have started that simulation. Of course, this simulations has run in the meantime, and today we are able to post-process the results. I'll quickly talk you through the first example, the e-machine cooling jacket, just to refresh your mind about the boundary conditions. So as you might still know from previous time, it's about a cooling jacket, and inside of this cooling jacket an electric motor is placed, and of course this electric motor needs to be cooled down. We haven't modeled the electric motor as full solid model. That can be done, but was a little overkill in this situation. And it's just represented as a heated wall on a red surface here. The material itself is printable aluminum, and the heat generation, which represents the electric motor, equals 700 watts. If you have a look then for the fluid, which is the blue region in this render, there are defined several things. Of course, first of all, the type of fluid is water, so just regular water, no additives or glycol mixtures or so, just regular water. It has an inlet temperature of 51.5 degrees Celsius and a flow rate of 3.8 liters per minute. So actually a very basic case, just a minimal of boundary conditions, but it's easy to show you how to do the case setup and how to do the post-processing. So we have submitted this simulations 2 weeks ago during the first Diabatix Summer Series webinar. Let's have a look now how the results look. So I have switched the screen so that you can see the Diabatix ColdStream platform. And what you can see immediately is, if you have a look to the project space, one of the projects that I created last time is the Diabatix Summer Series project. And you can see all cases are finished, and we have submitted 2. And now you can open the project and you get a detailed overview of the 2 simulations that we have submitted and that they are both finished. Let's start with the e-machine cooling jacket, and then you can immediately start with the first step of the post-processing, and that's just an analysis of some parameters. Most important parameters, of course. There's a case summary. And what you have there is an overview of the most important input and output parameters. I can, for instance, first of all, check the imbalances. You can check all the temperatures. So I'll note down here already that the maximum temperature of the motor is 61.3 degrees Celsius with a mean temperature of 57.4 degrees Celsius. These are, of course, the values that interest me most, together with the pressure loss, which you can find a little bit below. You also have an overview of some input parameters here, but these are just the parameters. Why is this handy, or why would you use this? It's first of all a very good way of quickly evaluating performances, because it's really only on the numbers. And secondly, it's a good way of evaluating your simulation, to quickly check if all the inputs were right and if the simulation did run well. What I usually do with this page when I need to go into a client meeting, or I need to go into a meeting with the upper management, is I just take some screenshots from here and I'll put them in a PowerPoint, which makes it a little bit easier in the meeting. Or I directly open this database or dashboard, let's say, of your simulation into the meeting itself. That's also possible. It's quite fast, so that works well. These are, of course, only numbers. When I've done a simulation, I also want to see, of course, some visualization of results, and that can be done in the 3D result tab. What will happen then is the 3D model of your simulation will load, and we will be able to do some post-processing here in this module. So the geometry is loaded. Let's turn it a little bit. Make sure that it's good visible. And then what you can see on the left hand side is some feature tree that you can explore, where you have all the solid geometries and boundaries which are defined in the case setup. Let's hide a few so that we can focus on the cooling jacket for now. And what you can do then is just click on the solid itself, or the surface plot of the solid, and then you will get a drop-down menu where you can change the color if you want, but where you can also color the surface of that cooling jacket with a certain field. Let's take, in this case, the temperature of the cooling jacket, since that's what I'm most interested in. And then you can see that there appears a minimum and a maximum scale, which you can change a little bit if you want, and a color scale with different ways of coloring for how you want to visualize. I like the blue to red one because it's the easiest for me to analyze a result. So for me, this render is good. I'll turn it a little bit, and again, what I will do then is I'll take some screenshots from this in order to put it into presentations for management, to discuss with the team or to discuss with clients. And it's very easy to do that, since there is a screenshot button. You can give it a name like temperature of cooling jacket. And then you can give it a transparent background as well if you want. And you can choose which format you want to have. And then it's simply clicking the download button, and the temperature, or the temperature plot, will be downloaded. Of course, temperature is not the only thing that I'm interested in. Let's visualize the fluid as well for a moment. And then you can, for instance, if you select that as well, visualize a lot of different fields, going from the pressure loss, which is always interesting to visualize. Let's turn it a little bit to see where the pressure losses are, and that's I believe interesting to analyze some results, to see where you have some recirculation or where you can improve your design in order to remove some pressure loss. And you can easily take a screenshot again Voila, so that's for the pressure loss. You can also visualize some other fields like the nu-t field, heat fluxes, if that's applicable, and so on. Another interesting feature of the post-processing module are streamlines. And you can give them a color as well, for instance, according to the velocity. And let's bring the scale down a little bit then. Voila, and then you can see where high and where low velocities in your design appear. Voila, and you can also turn on inlet and outlet patches to visualize. Let's say if you want to visualize the pressure over there, that can also be done. Okay, so that's the post-processing for the cooling jacket module. Let's have a look as well for the air-cooled amplifier. That one is a little bit more complex. The cooling jacket only consists out of one solid, one fluid, one heated wall, so it's fairly easy. But as you remember from the first webinar, the forced air-cooled amplifier had a lot more solids, a lot more heated walls, so also the post-processing will require a bit more of time. So before switching again to the platform, I'll quickly go through the boundary conditions overview again of this case as well. So you have a lot of different solids, starting with a manifold, which is the black part here, and a casing out of aluminum, and the heatsink itself, which is also out of aluminum. The heatsink from the bottom side is covered with an electronics cover, also out of aluminum, and underneath that cover there are some components, and there is placed an outlet filter for dust to prevent to get into the heatsink. Same with the manifold, there is some fan inlet in there. Behind the two fan inlets, it's not visible at the picture itself, there are two fans which blow the air through the case. If you have a look then to the resulting fluid, you have two fan inlets, and yeah, you can see the internal shape of the heatsink as well here. So it's just a straight fin design, and then you have the outlet at the back. You can see here all the components that I've shown in the assembly are incorporated in the fluid. So like for instance the filter is cut away out of the fluid, but we won't simulate all these components, or we won't take into account all these components into the simulation. We take it into account when creating the fluid region. But for instance, the manifold is out of plastic, just like the outlet filter. From thermal perspective, they won't have any influence on the simulation results, so we leave them out in order to not make the simulation too heavy. Of course, you can do this type of heavy simulations with Diabatix ColdStream, but if it's not necessary, you can easily exclude these components. Both of these fan inlets do have a fan curve, and I put it all the values over there. And on the bottom side there are 7 components. 6 of them are just represented by a heated wall on the heatsink itself. They all have a heat generation of 12 watt. And then there is a 7th component, and that's the most critical one, that has a temperature of 150 watt, and that's placed on a vapor chamber. This vapor chamber we have simulated as just a solid material with a very high conductivity. That's in this case a very reasonable assumption to make. Okay, so let's switch again to the ColdStream platform, and I have opened the project window again. so that we can open the second simulation and you immediately get again to the case summary. So let's analyze the results. Let's put it in degrees Celsius and you can immediately see for the first 6 components that all temperatures are around 50 degrees and that there is a slight variance over each component of more or less 2 degrees. The same for component 7, which is almost at 54 degrees, so a little bit warmer, but that's logically speaking, since the heat generation in that component is much higher. But you see that the vapor chamber did a very good job, since the spread on that component is really minimal. You also have some overview immediately of the outlet temperature and as well of the pressure and the mass flow rate of the fan. Of course, this is not an input in this case, since it's a result of the simulation because we have worked with a fan curve. So these are all things that you can check as well. You also have an overview of which heat inputs you gave. I think it's really nice in cases like this where you have a bit more components, because it's harder to remind. In the previous case you had only one boundary condition, so it's easy to remind that was 700 watts. But in this case it's a little bit more difficult because you have many components, and I can imagine that you have even much more complex cases that you want to simulate, and then it's quite handy that you just have some overview. So that was the case summary itself. Let's have a look as well to the 3D results in order to visualize it, and you can see again on the left hand side that you immediately see the structure which we have built during the case setup. So with all the different solids that we have simulated and the fluid region. I'll quickly remind you again, the full assembly did have much more solids, but we didn't simulate them all. We just simulated the aluminum heatsink, the casing which was placed on top of that heatsink, the cover which was closing the heatsink in order to protect the electronic components, and the vapor chamber. Okay, so the geometry has been loaded. Let's turn it around a little bit again. And let's hide a few things in order to only visualize the heatsink. So we only see the heatsink right now, and you can select it again and put it onto a different temperature. Voila. You can also again change the scale if you want that, or you can change the color of how the results are visualized. Let's take a screenshot again. And let's hide it. We can again take some pictures of the fluid as well. So let's select that and let's take the pressure loss again, and you can see perfectly how the pressure loss is distributed over the full case, and you can see, for instance, that there is a big pressure loss when the fluid enters or enter the fins. Let's make it transparent again as well. And what I really like right now is, for instance, that you can visualize the heatsink together with the streamlines. You can put the heatsink to a solid color again in order to put some contrast in, and then color the streamlines according to the speed, for instance, and that enables you to create some nice renders like you can see here. And let's put something else as well here again. For instance, on a different color scale. Just taking one rainbow, for instance. Voila. So, and that enables you to create some beautiful renders. The art of CFD, like we say. Okay, so let's hide the streamlines again. You could also color the two inlet patches, for instance, on the velocity that you have on that patch, or if you want to see which pressure you have there. If you come to the casing, of course, this component is much just closing, let's say, the heatsink, but of course it gives some contact surface as well. So we simulated it with it, since it also have a good conductivity. So we can also color that one according to, for instance, the temperature, like you can see here. And then you have the electronics cover as well, which you can also color according to the temperature. Last thing that I want to check is the vapor chamber. Since we approximated that vapor chamber just by a very good conducting solid, and I think we need to rescale a little bit to make some sensible results. Voila, and then you can see that the temperature distribution over that component is very well. I'll make a final screenshot of that. And I'll download that. Voila, so that's it. This was a webinar about time-efficient post-processing, where I demonstrated how you can do post-processing at the Diabatix ColdStream platform. I hope you enjoyed it. I'll quickly remind you as well that there are a few more webinars coming up into the Diabatix Summer Series. So we have covered the first two. In 2 weeks, my colleague Reshma will create a design with generative design technology for the cooling jacket that we have simulated today as well. So the design that I've shown you today was just a conventional design. Reshma will now show you how you can optimize this. And in the last summer series, my colleague Dr. Van de Beek will go more in depth about boundary conditions. So we have covered a few easy boundary conditions in the past webinars already, but she will go more in depth, more in detail about more complex boundary conditions, like for instance radiation. So don't forget to register for this website, for these webinars via our website. Also, if you want to rewatch one of the webinars, the webinar of the day, or the first one in the webinar series, or one of our regular webinars, feel free to do that at our website. And if you might end up with any questions, don't hesitate to contact us directly or send us an email. I would like to thank you for your time today and for attending this webinar. I hope you enjoyed it and that you got some insights on how you can do some time-efficient post-processing. And I hope to see you again in our following webinars. Thank you very much for attending.